Welcome to the Silicon Learners. In the last video we saw how a bad combination blocks become a latch. That's a dangerous in hardware. So how do we design circuits that remembers things safely? Okay, we use FSM. FSM is finite state machine, and FSM is just three things: states, inputs that cause state change, and outputs. Today we will see the two types of FSM. Type 1 is Mealy FSM, and second type is Murray FSM. So what is difference between Mealy and Murray? So basic difference between Mealy and Murray FSM is Mealy FSM is depend on states and current input, and Murray FSM is only dependent on the current state. Okay. So first of all, we'll see what is the FSM is finite state machine. Okay, finite state machine. What is meaning of finite? So finite is a source limited states like idle, read, and write. And already I tell you Mealy and Murray difference. Okay. So we will go on code and see the difference of Mealy and Murray in the simulation. Okay, let us go on our code. This is a code of 101 FSM. Okay, so how we will write this code? So first of all, to write this code, we have to design a state table, state diagram for the 101 sequence detector. So here is state table. Here we have three state, S0, S1 and S2. We denoted S0 as 2 bit 00, value of S1 as 2 bit 01, and value of S2 as 2 bit 10. Okay, in state diagram we can see when we will give input 1 at the S0 state, the output will be 0, and our next state will be S1. Same as for input 0, our state remains same and output will be 0. When we are at the S1 state and we give 0 input, our next state will be S2 and output remains 0. Same as if our input is 1, output will be 0, and it remains in state S1. At the S2, when we give input 1, our output will be 1. It shows our sequence 101 will be complete and output will be 1. Same for if we give input 0, the output will be 0 and next state will be S0. Okay, so this state diagram we are simply applies in our code. Okay, here is our model name Mealy 101. Here we denoted value of S0, S1, S2 using parameter keyword. Okay, in the always block we define when our positive edge of clock or positive edge of reset, then this block will be executes. For if reset is high, the state will be S0, and if reset is not high, our state will be next state. So what will be our next state? For this we define again another always block. It is our combinational logic. Okay, so as per we see in this state diagram, we simply define at this code. Whenever we are at S0, next state will be S1 if D in equals to 1, means our data in equals to 1. If data in equals to 0, our state will be next state will be S0. Same for if we at S1 and our input is 1, so our next state will be S1. If input is 0, next state will be S2. Same for S2. Our if our D means data input will be 1, the next state will be S1. If D data input is 0, the next state will be S0. So this is code, and here we define when our D out is 1. Here it defines when D out will be 1. So it will be 1 when the state equals to S2, means 2 bit 01. no sorry 2 bit 10 and input is 1. So this when these both conditions satisfy, then the our d out will be 1, means data output will be 1. So we will see this in the our waveform. Okay, so here is our waveform window. We just open it. Here is our all objects we have to add in the wave. Okay, here is our waveform window. I zoom it. Okay, now we have to first provide a clock, so we will provide clock, then we will run our simulation and we can see here clock comes. Now we will provide our sequence 101. So first of all we will force value of data input equals to 1 and run the code. Then we will again force value 0 and run the code, and again we will force value 1 and run the code. Okay, we have to again provide the sequence, because at the when our first positive edge of clock, the we not provide the data input, means our data input in high impedance state. We will cover in the next video, next upcoming video about it. So we have to again provide this sequence. And we can see here is our output goes high according to code logic. Okay, now I will explain in the wave what happened. So as per I said, at the starting of edge of clock we not provide data input or reset, so it is high impedance state, so our outputs are don't care. Okay, so it starts from this edge of clock and we can see our sequence. Here is 1, so our next state will be 0 1. It shows here at next edge. Again we will see our state is 0 1, which we see at previous edge of clock. And at this edge of clock, when our data input is 0, our next state is 1 0. Okay, so this state we will see at next edge of clock, and we can see at this edge of clock our state is 1 0. Okay, so here combination of 1 0 1 sequence completed, and our d out data output goes to high, means data output is 1. So this is satisfy our condition which is described in our code. State is 1 0, right? We can see when the state is s2 means 1 0 and d in data input is high, our output will be 1, which can see on the waveform where our state is 1 0 and data input is 1, our data output is also 1. So this is a Mealy FSM where the output depends on state and the d in means data input. Now we will see Moore FSM, how it is different from Mealy FSM. Okay, let us see. Here is code of Moore FSM, and I will show you the state diagram of Murray FSM. So here is state diagram of Murray FSM. Our states are S0, S1, S2 and S3. Observe these states in the Murray FSM. One state is more than the Mealy FSM, and we denote S0 as 0, 0, S1 as 0, 1, S2 as 1, 0 and S3 as 1, 1. Okay, so here is also same logic applies. When our input is 1, it goes next state. When the input is 0 at the S1, it goes next state S2, same as a Mealy FSM. But what is basic difference between Murray and Mealy is Mealy depend on input. Mealy's output depend on input and Murray's output not depends on input. So in the Murray, that's why we need another one more state for provide the output is 1. Okay, so let us see the same behavior in this code. You can read this code. This is our always block when the state where we defines state equals to next state, and this is our combinational block where we defines what should be value of next state, and this is our another always block where we defines when the output should be 1. Here notice that we defines the output as a 1 at the state equals to S3, means when the state is 2 bit 1 1, our output also will be 1. Okay, so let us go on the waveform. Here is objects we have to add on the wave. Here is, and we have to provide the clock first. We will provide input is 0. Sorry, first of all we provide data input is 1 and run. Again we will provide data input as a 0 and we will run, and we will again provide data input as a 1. Okay, and run. Now you can see our sequence 1 0 1 completed, but we not see the output as a 1. Why? Because it will be 1 cycle delay. See this, at this next stage of clock we can see our output. This is the basic difference between Mealy and Murray FSM. Murray FSM will be give output at the next positive edge of clock when the sequence occur, and we see in the code when 101 sequence occur, but output is not goes 1. Okay, so this is basic difference between Mealy and Murray. And we see at the next stage of clock, here our output goes high, so we will notice our states. Okay, so let us see it. When the input is 1, our next state is 0 1. At the next edge clock we see our state goes at 0 1, and at the same edge of clock our next state is 1 0. At the next stage of clock our state goes at 1 0. Okay, and next state is 1 1. So at this edge of clock our current state is 1 1 and next state is 0 1. Now goes back to our code logic where we defines when the state is S3, means 2 bit 1 1, our output should be 1. Okay, so see this, our current state is 1 1, but output is not 1. Why? Because it is depends on next stage of clock. So here next stage of clock arrives. At this clock our state is 1 1, and flip-flops in flip-flops memory store it, and at the next stage of clock our output goes high. So this is the basic difference between Mealy and Murray we see on the waveform window, okay, in the simulation. Now in the next video we will we will see and learn about how we can write the FSM codes. There is three process of to write the FSM code, which is called one process and two process and three process. So we will see in the next video how can we do this. Thank you.